a fantastic start on this instrumentation journey that I've been on. As Suzanne mentioned, I've been working with instrumentation for a while, starting with scouting sites for the EarthScope transportable array, and that has gotten me into a path where I now manage a lot of the permanent stations installed all around the United States. So yeah, there's a lot of things behind the curtain that go into delivering seismic data to your desktop. So I want to give you a little bit of an idea of how that's done and how, we actually go from the earth shaking to the digital signal that you are able to acquire and process on your laptop or desktop. So I'm going to start pretty basic. Thank you to everyone who responded to my survey in Slack. It looks like we have quite a number of folks who are experienced with installing instrumentation, possibly with working with metadata. So I welcome your questions towards the end of the lecture, or perhaps after we've gone to the breakout rooms. I think this is going to be a sort of a very quick overview of a lot of things dealing with instrumentation and metadata. And I welcome your questions anytime. So I put these questions up as we get started to kind of bring things, make them more relevant to you for your research. And it looks like there's quite a diversity of research in this group, which is wonderful. Asking you to start out thinking, what's the frequency content of the signals that you're usually working with? What is their amplitude? Are they small ambient ground motions? Are they huge earthquake signals strong enough to collapse buildings? And then when you measure those signals, how accurately do you need to know their amplitude? So do you need to relate those to the actual physical units of ground motion? And how accurately do you need to measure their phase? So arrival times or the phase of surface waves, for example. Every different research project has different requirements for these. And as we go into metadata and dealing with instrument responses, you may have very different requirements from these than other people in this group. So it's good to think about how this applies to your research specifically. So a couple of examples of these quickly to start off. If you're doing tomography using surface waves from large earthquakes, you're probably working at long periods. So in that case, it would be maybe above 20 seconds. You're looking at large signals relative to the ambient noise in your installation, hopefully. The phase of those signals might be really, really important for you. And the amplitude, you want to know what the amplitude is, but that's less important than the phase of those signals. On the other hand, if you are locating earthquakes by picking body waves, you're probably working at higher frequencies. You have really wide variation of signal to noise ratios, right? So if you're trying to pick very, very small earthquakes, you might be just above your site noise. The phase and timing of that arrival is really, really important. And you might not even care about relating that to physical units of physical ground motion, right? You might be picking on the raw waveforms that come straight out of your digitizer, and that's perfectly acceptable. So again, it's good to know the requirements of your application when it comes to working with metadata. All right. Okay, so let's go ahead and get started. There's a lot of things to cover today. I want to acknowledge that a lot of the slides in this course are material that was adapted from a tutorial developed for a data processing course by Suzanne and Bob Woodward of IRIS. So thank you guys for sharing that. It's been massively helpful to me, and looking forward to sharing it today. All right. So I always like to start off lectures with some take-home points. So if you tune out for the rest of the lecture, this is what I would like you to remember. Instrument responses look complex, but they are not a mysterious black box that you have no chance of understanding. The stages of an instrument response just describe the process of taking a physical ground motion and converting it into a digital signal. When you are working with instrument responses, you need to choose your processing parameters very carefully, depending on your specific application. So what works for one person might not work for you. I like to tell people you should never rely on the defaults in the OBSPI code that we're going to be looking at today. It does a decent job, but it's probably not exactly right for your application. So it's important to sort of look carefully into things and read documentation and think about what exactly am I trying to measure and use this metadata for. I also want to give you a little bit of an idea of kind of the breadth of seismic instrumentation that's out there. And it's really important to understand for a given instrument what it's capable of measuring and what its limitations are. So those are your 3 take-home points. I want to say I'm always happy to discuss more about instrumentation and metadata. A lot of the literature on this can be very difficult to understand, even for specialists. So I'm happy to answer your questions. My email address is up here. Please feel free to email me or chat me in Slack, and I will try to answer your questions. The last thing is my colleagues at ASL and I are working on a EduQuakes manuscript that discusses a lot of things that we'll be covering today. So if there are questions you have that aren't answered or something that you would like to see answered in a little bit less technical instrumentation specialist way, please let me know, and that will be really helpful to us as we're writing this manuscript. All right, so you're a researcher, grad student. Why do you specifically need to know about instrumentation and metadata? Well, again, a lot of you, it seems, have actually installed your own instruments, so you have hands-on experience with this, and you probably know a lot about that specific instrument, and that's fantastic. Seismology does have a history of freely sharing data, so that means that you can go to IRIS or your favorite data center and obtain data really easily from a very wide variety of seismic instrumentation. That's a great thing because it means that you have access to all of this data, but you also need to be aware of how that data is acquired and if you're using the right tools for the job or not. So you need to be able to understand the instrumentation that recorded that data and what it can and can't do for you. You also need to be able to look at metadata and use it correctly to convert those raw digital signals to physical units. All right, so here's a quick snapshot of 3 very different kinds of stations with different kinds of instrumentation. So on the left, many people might be familiar with working with data from the Global Seismographic Network, or GSN. So this is a global network of extremely high quality, long-term observations. It's used for both research and monitoring. And the sort of the specialty of the GSN is producing really high quality, long period data. So if you're looking at signals at periods above 100 seconds, the care that is taken in selecting instrumentation and in installing it in the GSN will make sure that you have the highest quality data. Stations like the ones that I manage inside the US, these are designed mostly for monitoring. So we're trying to monitor to detect and locate earthquakes, ideally magnitude 2.5 and above, anywhere inside the United States. And the network is designed to provide uniform coverage across the lower 48 states, coordinating with denser regional networks. So you can see here, this GSN station is installed in a borehole. This is a station at the South Pole in Antarctica. Here we have a different kind of instrumentation. So this is a borehole sensor here. This is a vault style sensor. This vault is actually a strong motion sensor. So we have a strong motion sensor here and a broadband sensor over here. And this is not going to record the same long period data as that really, really quiet GSN station, but it's sufficient for regional monitoring needs. And then finally, if you go over here, looking at those portable stations that Suzanne mentioned earlier, this is a very light and fast kind of instrumentation. So you can see we have much smaller vaults that are buried much more shallowly. And the target that we're looking at here is to get out quickly. So you can see we can just direct bury these vaults, no concrete needed. We're trying to densify coverage in an already existing network to get better estimates of earthquake locations and depths. And we also have strong motion instruments in these because we're trying to record strong motions for hazard studies. So these are just 3 examples of the very different types of seismic instrumentation that you might find at a different station, right? So if you were trying to study normal modes from, magnitude 8 earthquakes, you're going to use the GSN. Our little portable stations are not targeted at observing those kinds of signals. Okay, so let's start with the basics. What exactly is an instrument response? So again, like I was saying, this is just a way of describing the process of taking a signal from
Emily?
motion. Yes?
Before we go forward, we have a question.
Yeah.
How high and low can a GSN station go comfortably?
Ooh, what do you mean by high and low?
Let's pause and see if
Okay.
our question can clarify. I'm thinking frequency, but let's see if they have where is the flat response?
Okay, good question. So the broadband, the primary broadband sensor at a GSN station is usually flat out to at least 240 seconds, often 360 seconds. And that's just the flat passband of the instrument, which we'll go over in a minute. You can record much longer period signals, even if you're outside the flat passband. And we put a lot of work into carefully calibrating these stations so that the amplitudes remain accurate, even if you're in the roll-off at longer periods.
And Emily, I had a follow-up question on that similar subject. I'm thinking about the EarthScope transportable array. Mm-hmm. Like in this framework of 3 types of stations you've listed here, where would those stations fit in?
Oh, that's a fantastic question. So those are somewhere between the portable stations and the permanent stations, right? So the EarthScope transportable array, these stations were originally designed to be installed for 2 years. So they basically have actually a deeper vault than many of the US permanent stations have. So it's a plastic vault buried about 2 meters into the ground. And they use similar kinds of instrumentation, so an STS-2 or other sensor that has a response out to about 120 seconds. And the construction, so the instrumentation was more similar to a permanent site. The actual construction is more similar to a portable site. The USGS adopted 143 of the TA stations, and they're now operated as the N4 network. So we adopted about 1 in 4 of the TA network code N4. And that's one of my challenges in my job right now, is how to take these stations that were originally installed to be temporary for 2 years or so and convert them into permanent stations. So that's, yeah, that keeps me quite busy. Does that answer your question?
Yes, thank you.
Okay, awesome. Good question. Okay, so instrument responses. Actually, this is perfect. Here's a picture of a TA vault right here. So this is a average sized human being standing inside it. And you can see what looks like an STS-2 down at the bottom here. So the instrument response just describes the process of going from ground motion all the way to the waveform that you get on your computer to analyze. And so here's that whole chain. We're going to be talking about the part of it that's in the red circle. So we start with ground motion. That's recorded by a seismometer that has a mechanical response, and that's described by poles and zeros, if you're familiar with those. If not, I'll talk about them briefly in a minute. It has an electrical response, and that seismometer outputs an analog voltage that goes into a digitizer, right? So here's our seismometer here. It's got a cable that runs to the digitizer, and that digitizer takes the analog voltage and turns it into a digital signal. As part of that process, it applies something called FIR filters. These are finite impulse response filters. We'll talk about those in a minute. So now you have a signal that is in terms of counts instead of a voltage. And that is packaged up with some additional data in a format that we call mini-seed. There are many other formats of seismic data, but mini-seed is commonly used by data loggers. If you use RefText, they have their own data format. Your data logger sends that data to a data acquisition center. That data acquisition center, such as ASL or a regional network operator, might send that data onward to a data management center, such as IRIS. We manage the metadata for that station. So there are some newer types of instrumentation that will actually self-generate their own metadata. But historically, it's been the network operator who's responsible for knowing what kind of instrumentation is in their network and generating metadata for it. So we send the data and metadata to a data management center where you can request both the waveforms and the metadata. So this part here, going from the data logger to the data acquisition center, that's telemetry. That's my daily headache. We won't talk about that for today. We're going to talk about the process of going from ground motion to a signal in counts. All right. So mathematically, we can think about a seismogram output by the digitizer as a convolution of three different things. It's your source, so that might be an earthquake or storms in the ocean or whatever your signal is that you're interested in. That gets convolved with the structure that those waves pass through. And then finally, that gets convolved with the response of your instrument. All of these three things convolved together result in the seismogram that comes out of your digitizer. So we can think about this as a linear system, right? We input some signal, x of t, goes through a linear system, and we get an output signal. So our output signal, y of t, is the input convolved with this linear system, or if we prefer to work in the frequency domain, which is very often useful, then this is just a multiplication of the in the frequency domain. In other words, when we talk about an instrument response, what we were talking about is the response of this linear system to an input that is an impulse, so a delta function. So this contains sinusoids of all frequencies, right? We add these up, get a delta function. So when we talk about the instrument response, we're talking about the response of this system to an input impulse. And this produces the plots that you may be familiar with already. So we like to plot this up as the response of a system with frequency in terms of both its amplitude and its phase. So this is a plot for two different kinds of seismometers. One is a Raspberry Shake geophone. So it's a fairly short period system. And you can see that it has a constant response at these frequencies. And then the response of that system starts to roll off and get smaller and smaller at long periods. This blue curve here is the response of, I believe it's a CMG 30T. It's operated by the geophone network. And you can see that this has a broader response in frequency, right? So our long period roll corner here is it's at much longer periods than the short period geophone. So for the same input, these two seismometers will have a very different response. So that's the amplitude response. Looking at the phase response here, right? So this is the imaginary part of that response. We can see that the Raspberry Shake has a very different phase response than the broadband here. So if you wanted to compare these two signals directly, it's very important to account for both the amplitude and the phase response, because this large jump, it doesn't actually spike like that. It just wraps around from pi or minus pi to pi. That's going to make your raw signal look very, very different than this broadband curve here.
Hey, Emily?
Yeah.
So I'm trying to conceptually imagine what this difference in phase, how that manifests in the signal. Is it literally going to look like a phase shift?
Yes.
Like a time domain? Like I can understand the amplitude, depression, and whatnot, but yeah, so it's just a time shift
Yeah, it will actually look like a shift. So if you were looking at something around this frequency, if you input a pure sine wave, and I have those slides, but I didn't include them. If you input a pure sine wave, they'll look like they have a very different phase shift. So if you were measuring, for example, surface wave arrivals on a Raspberry Shake, which you shouldn't do, but if for some reason you wanted to, it would be very important to account for the phase there, right? You might be able to get away with it on the broadband because it has a fairly small phase shift here, but it would be really important to account for the Raspberry Shake's large phase shift. Does that answer your question?
It does, and we have a couple questions in the chat here.
Okay.
The first is why is the response only important in the flat region? And I guess you mentioned this a little bit earlier that it's actually potentially you can use the signal when you're outside of that region. But I'm not sure if you wanted to comment on that more. And then the second one was at frequencies beyond the dashed blue and green lines, the signals won't even be recorded for either instrument, is the other question.
Okay, yeah, great questions. So the first one, the response, talking about the flat part of the response, this is an indication of what this sensor is designed to record, right? So you can certainly measure, you can certainly measure signals outside of the flat part of the response, right? As I mentioned before, GSN stations have their flat part of the response goes out to about 360 seconds at most. However, you can measure much longer period signals with these up to normal modes or even earth tides, 12 and 24-hour periods. But you really have to be careful to make sure that you know exactly where that corner is and where the roll-off is. And we'll see why that matters when we do the deconvolution. But basically, if you are working where you have a very small amplitude response, when you remove the response, you are dividing by a very large, you're multiplying by a very large number, and that can cause things to blow up and your deconvolution to be unstable. So we'll get some hands-on experience with that in the lab. So knowing the flat part of the response, this is saying, okay, if you really want to record surface waves, right, you should probably pick something that has a good amplitude response at those frequencies, but you can push it a little bit with a well-calibrated instrument. Okay, and again, we'll explore that a little bit more hands-on. I think it's easier to understand once you've done the deconvolution yourself. The second question, frequencies beyond the dashed blue and green lines, signals won't be recorded. That is correct. So in these plots, that's showing the Nyquist frequency. So you can see that this blue signal is recorded at a higher sample rate than the green signal. And so we have no information at frequencies above the Nyquist, right? And so if I decided to decrease the sampling rate on this channel, then this roll-off would happen at a lower frequency. Cool. All right, so following on that linear system response, right? We take our input signal, which is ground motion here, put it through our linear system, which is our seismometer and digitizer. And we got our output signal, which is the seismogram in counts that comes out of your digitizer. So if you need to remove the response and go back to a seismogram in units of ground motion, if we're working in the frequency domain, You divide your raw seismogram by the impulse response or the transfer function in the frequency domain of your seismometer and digitizer system. So the way that I like to visualize that is you're flipping the instrument response, right? So instead of multiplying a signal by that, now you're dividing by it. So you're inverting that instrument response. And that's why this is important. So if you have very small, like low frequency signals, right? And you suddenly multiply it by what is now a very large number, you're going to blow up that noise, and that can introduce artificial long period noise in your signal if you do not know the response of this instrument very well at long periods. Can you get the original signal if you don't know the instrument response? You can't. You must know the response of your instrument if you want to get an output seismogram in units of physical ground motion, right? So meters per second or meters per second squared or displacement in meters, whatever you like. But that raw signal that comes out of your digitizer, you must know the response of that system if you want to be able to retrieve units of ground motion. And again, for some applications, converting to physical units doesn't matter. If you are measuring body wave arrival times, you just need to know the time that arrives, that signal arrives. You do not need to know how the amplitude of that P wave. If you're measuring earthquake magnitudes, then yes, the amplitude of ground motion does matter. So again, it depends on your application.
Hey, Emily, I had another question actually about these dashed lines.
Yeah.
So that, if I'm interpreting this correctly, these are, this is a digitizer sort of effect, right? Where you're controlling the sampling rate. But I'm wondering on the upper end of the frequency spectrum, if the response also, like if say you had a really high sampling rate,
Mm-hmm.
like do you see some sort of instrument response on the high end?
Yes. Well? Yeah, so you see an instrument response and also a digitizer response, and that's awesome because it's setting me up for my next section. So thank you for asking that question. All right, so I want to revisit an example that Sydney showed last week. So again, as we mentioned, deconvolving the instrument response is a division in the frequency domain. Remember that these are complex quantities, right? So your spectrum of ground motion, or your input signal, and your instrument response, these are both complex, but we like to look at just the amplitude part of that response to make it a little bit easier to visualize what's going on. And as Liam just pointed out, he noticed this high frequency roll off as well. So most of the time when we talk about an instrument, we talk about it in terms of where the long period corner rolls off. This is a GSN station at Tucson, so it's got a pretty long period corner. But there's also this drop, very steep drop at high frequencies, right? So what exactly is going on there? And some of you might know already, but in case you don't, we're gonna talk a little bit about what goes on inside the digitizer and why you need to be careful about that high frequency drop off. So here's the high frequency response of 3 different types of seismometers that were used within the transportable array. And these are commonly used in national and regional monitoring networks, as well as portable deployments. So we have Geralp 3Ts, Streckisen STS2s, and Nanometrics Trillium 240s. So you can see that the 3T and the STS2 both have a long period corner around 120 seconds. This Trillium 240 has a slightly wider flat band that goes all the way out to 240 seconds. They also have very different high frequency responses. And this is something that, as people are starting to push into higher and higher frequency applications, more care is being paid to those. And they also have, I think this is just showing the seismometer response here, but you can see that they all start to roll off at high frequencies. If you want to check out the response of another instrument that's not shown here, IRIS has this great nominal response library. So these are the responses of the instruments as supplied by the manufacturers. If it's really important to you to have high frequency data that's accurate to within a few percent, you should probably be running your own calibrations on these instruments or asking the network operator if they calibrate them. Because in many cases, the nominal response can have a misfit of a few percent to the actual instrument. And this is based on changes in manufacturing and different generations of sensors and things like that. Okay, I think I'm going to skip this for now. You'll get to obtain a response and plot it using OBSPy in the lecture, or sorry, in the lab. But let's talk about the process of taking that analog voltage from your seismometer and actually turning it into a digital signal. So we start with our analog signal, and this goes into your digitizer, and it is sampled at an extremely high sample rate to begin with. And then it is filtered and decimated down to a lower sample rate. So you want to sample at 40 samples per second. There are actually several stages of decimation and filtering to get that analog signal into an unaliased 40 samples per second signal. So we describe this as a cascade of filters, and these are all designed to avoid anti-aliasing. So we start with a signal. In this case, it would be sampled at 320 samples per second. We filter it and resample, filter it again and resample, filter it again and resample. In this case, the end sample rate is 20 samples per second. So this avoids having high frequency signals aliased into the frequency band that we're actually interested in. All right. So this is the cumulative effect of all of those anti-aliasing filters that are occurring inside the digitizer, right? And if you are looking at a seismic channel sampled at 20 samples per second, you don't want any of those higher frequencies leaking into your data. So the digitizer applies that cascade of filters for you. In the case of the TA, here's an example. They represented the entire chain of filters with a single filter. And you can see the cumulative effect of that is to drop the frequency response at high frequencies down to nearly zero. If we zoom in on that roll off, you can see that we have a little bit of ripple, right? So this is very common looking at Fourier analysis. If you need something to have a sharp drop off, right? Thinking about a square wave and that Gibbs overshoot phenomenon, same kind of thing. You'll often have a little bit of ripple near those very sharp corners. It's usually less than about 5%. But again, if accurate amplitudes are important to you, you really want to be avoiding these high frequency effects. So that's my little aside about finite impulse response filters. These are related to digitization. Very often you can ignore them. My personal rule of thumb is that if I need to, the highest frequency that I should be working with shouldn't be any higher than 50 to 75% of the Nyquist frequency. So if I am working with a signal sampled at 40 samples per second, my Nyquist frequency is 20 hertz, and I really don't want to make any measurements higher than at about 10 to 15 hertz, and that's even pushing it, right? Because again, if you are working near that high frequency drop off, if you try to remove that response, suddenly you're multiplying by a very, very large number, and that can cause all kinds of unwanted effects. Okay, any questions about that section so far? I'm going to move a little bit into a different topic and talk about seismometers recording things other than seismic signals. Okay, you'll get a chance to play with response deconvolution and work with some of these effects in the lab. It's a pretty open-ended lab, but I just want to give you time to play with OBSPy and see how a lot of these different processing options can introduce artifacts or pick out the kinds of signals you want in your data. Okay, So moving on, I want to point out that seismometers, in addition to recording ground motion, as I'm sure many of you know, also record a lot of different other signals. So in choosing sites for a station, one thing that we very frequently try to avoid is cultural noise. So here's a list of siting criteria for the EarthScope transportable array. And based on that, the siting criteria that we used for the SPRI portable deployment. So we were trying to avoid things like roads, railroads, highways, trains, anything that's occupied, tall structures that might move around in the wind, construction, fast-moving water or dams, things like that. So these are mostly, we call these cultural noise sources because they're mostly generated by humans, and those tend to be higher frequency signals. If you've been lurking around on Seismology Twitter in the last couple of months, you might have seen these very fascinating plots showing the drop in high frequency noise levels in this cultural noise band due to lockdowns around the world from COVID-19. So here are two really striking examples. This is a permanent broadband site in Brussels where this was first observed by Tom Lecoq. And you can see there's a lot of daily variation in high frequency noise. And then after lockdown is imposed, this drops sharply. Here's another really nice example from a Raspberry Shake installed at a school in Western Nepal from Shiva Subedi. So this is recording, most of the time, this is recording humans causing ground motions, right? People walking around, cars driving by, things like that, air conditioners, generators. But after lockdown, the level of noise that the seismometer is observing has drastically dropped. In a different frequency band, seismometers all over the globe record waves in the ocean, storms in the ocean. We call this the microseismic band. So we have sort of a constant earth hum, this band between about 2 and 20 seconds roughly. Sometimes this will pick up on a specific storm. This is a cool example from Hurricane Sandy several years ago. But no matter where you are on Earth, you're going to see the signal from the ocean, which is pretty cool. And I'll talk a little bit about what about these kinds of plots here in a moment. And finally, you can get a lot of other long period signals from things that are completely unrelated to seismometers. So here's one example of one of our data quality analysts. We have a sensor right next to a cow pasture, and every time that rancher moves his cattle near the seismometer, we see these long period tilting signals occurring on the seismometer. And that can look like the actual sensor itself is failing. But if you are sitting right next to the seismometer and you see a cow walk by, you can actually watch the ground tilt, or even a person, if your sensor is shallow, you can watch the ground tilt as that force is applied to the ground next to your vault. Another cool thing that you can see on seismometers that is not generated by earthquakes or anything tectonic is if you have shallow vaults, you can actually observe the deformation of the Earth's surface as a storm passes over. So the transportable array stations had co-located barometers. So when a storm front passes, you can actually see a change in pressure from low to high. And this actually manifests itself as a tilt, long period tilt on a seismometer that's buried relatively near the surface, right? If you have a borehole sensor that's tens or hundreds of meters deep, you won't be as sensitive to these kinds of surface effects. All right. Very often when we talk about seismic noise, oh, see a question. Okay, sorry, not related to this. Okay, so very often when people are talking about seismic instrumentation performance, we'll plot these noise models that were developed by John Peterson in 1993. So he plotted up a bunch of power spectra from high quality permanent network sites and basically drew a line saying this low noise model is the quietest environment that I expect to see at a well-installed station anywhere in the world. And this high noise model is sort of the upper limit for what I would consider to be a useful station in terms of sort of global monitoring applications. You'll very often see signals in the microseismic band exceed this. But these are sort of our two baselines that we like to use to say, you know, the station is performing well, or it's too noisy, or something like that. If you ever plot up a power spectra and see it well below the low noise model, you might have a problem with your instrumentation or with your response. To give us a little bit more, a little clearer idea of the noise characteristics of a station, we very often compute these power spectral density compute power spectra and then compile them into probability density functions. So this is a way to answer the question, okay, for a given time period, how often do I see a certain level of noise at a certain frequency, right? So we can see here, this is the microseismic band, this is that ocean signal. We see a very consistent signal from about 1 to 10 seconds, right? And in this cultural noise band, we see a large variation that's almost bimodal. We have a lot of low power spectra, but also a fair number of higher power spectra here. So this gives us an idea of sort of distribution of noise levels with frequency at a particular site. So we can see that overall, this is a pretty well-performing station. This is a station in a remote part of Idaho, up in the mountains, so it doesn't get a lot of cultural noise. And it's pretty well installed, so it's fairly quiet at long periods. And these kinds of plots are widely used in network quality control. I do want to point out that the choice of processing that goes into this, right? So this process involves taking a seismogram, slicing it up into overlapping segments, and then smoothing the resulting power spectra. Those choices of windowing and smoothing should be very carefully tuned to what you're trying to monitor. The original algorithm that was described by this McNamara and Wolin paper, that's appropriate to use for network QC, but if you are trying to do things like studying the variation of cultural noise or the changes in microseism amplitudes over time, you need to make sure that you're using parameters that allow you to resolve those. And there's a good paper out recently by my colleagues, this should be 2020, not 2018, on how to choose those windowing and smoothing parameters for your power spectral density plots. Okay, so again, just a quick summary. I think everyone has their own idea of what short period, long period signals are, but here's what I generally mean when I talk about short periods or long periods or microseisms. So short period noise, generally 1 to 10 hertz, is most often caused by human activity or small local earthquakes. The microseismic band is caused by storms and waves in the ocean, and long period noise, your long period signals are things like surface waves, but your general ambient noise background is usually your local site responding to changes in atmospheric pressure or temperature or things like that. So as you're installing a seismometer, yes?
We have a question before you move on.
Mm-hmm.
Should you process the raw waveforms to compute PSDs or PDF?
Yes. So in order to compute a PSD PDF, what you need to do, you take your raw signal, you need to have correct metadata for that station, and then that is applied. You'll notice that the units of power over here, although they're a little, they look a little crazy because they're expressed in units of decibels, this is an acceleration power spectrum. So this is taking that raw signal and converting it into acceleration and then applying the transform that makes it decibels. But in order to compare with your with the Peterson noise models, these black lines here, it needs to be in units of acceleration. So yes, you must apply the metadata in order to make these comparisons. If you were comparing, if you just want to look at the relative change at one station, you don't necessarily need to do it. But if you want to compare noise levels between stations or between a station and a defined noise model, then yes, you must use metadata. Okay. All right, so to finish, wrap up on this slide here, if you want to mitigate different sources of noise, your short period noise, you can usually minimize that by carefully selecting your site so that it's in a remote location, or to some degree, how deep you install your borehole or your post hole if you have a choice to do that. Long period noise, the best way to minimize that is careful construction. So you want to minimize the amount you're disturbing the ground, bury it as deep as you can, make sure you have a lot of thermal mass around your sensor. And in terms of microseisms, you're pretty much stuck with whatever is happening at your site. If you're close to the ocean, you'll see very large signals. The further inland you go, the smaller amplitudes you'll see for microseisms generally. But this is more a characteristic of propagation through the earth than it is anything that's extremely local to your site. Okay.
Hey, Emily?
Yeah.
I had a question about tilt noise.
Yes.
So I know there's a lot to be said about it, but is it only a problem on horizontals or is it also a problem on verticals? And why? Yeah, can you just unpack that first statement there a little bit more, please?
Yeah, absolutely. So yes, tilt is an issue at long periods, and I'll put a link to there's a good write-up of this in the new manual of seismological observatory practice that's put out by the GFZ in Germany. But basically, it has to do with the fact that a tilt maps much more onto the horizontal components than the vertical. So if you have a well-leveled sensor, tilting the ground will show up on that vertical axis much less than it will on horizontals. Yeah, so you'll see a small amount of tilt on the vertical, but it's really the horizontals that are sensitive to any local deformation.
Thank you.
Yeah. And again, those tilt signals produced by local surface effects, those decrease with depth. So if you're looking at a GSN station that's in a deep borehole, you'll see much less tilt than you would at a very shallow station. These PSDs in the background are from a SPRI station. So you can see the vertical on these does pretty well, but these are buried only a meter deep in a vault. And so the horizontals tend to move around a lot because these are installed in very soft sediment. Okay, moving on here. I'm loving the questions. This is excellent. So I might run a little bit over 11, but I'll try to wrap up quickly. Okay, one thing that I think a lot of folks don't think about, and I certainly didn't much when I was a grad student, is the self noise of the instrumentation that I'm working with. So this is defined by the combination of your instrument and digitizer. And what this is telling you is the smallest signal that you can resolve based on the limits of your instrumentation, right? So that digitizer is going to have a little bit of digitization noise in the electronics related to converting that analog signal to a digital one. And your seismometer is also going to have a certain amount of self noise just in the fact that it has a mass that might be moving around slightly. A seismometer with larger masses might have lower self noise than a seismometer with the smaller masses. And the really important thing that I want to drive home here, I can't go into self noise much, but self noise is different than the passband of the seismometer. So two instruments can have the same response shape, but different self noise levels. So here's an example shown here. So this is a Trillium 120 volt seismometer. It's about the size of a bowling ball or slightly larger. And here is a Trillium compact seismometer. Same manufacturer, this is about the size of a can of soda. And although they have essentially the same response, you can see that the two examples I picked here have different sample rates again, but they have the same long period corner. they have very different self-noise. So the plot we're looking at here is power versus frequency. So we've taken that Peterson noise model and flipped it around. So here's our microseismic band here. And you can see that this Trillium compact has higher self-noise at long periods than other broadband sensors. So here's that Trillium 120 here, this kind of green dashed line. And what this is saying is, although they have the same response shape, this Trillium compact can not resolve the same tiny, tiny low amplitude signals that this Trillium 120 can. Right, so if you wanted to resolve extremely small signals at long periods from distant earthquakes, surface waves or something like that, a Trillium compact would not be the correct instrument to use. Those signals might be below the self-noise levels of the Trillium compact. On the other hand, if you're a regional network operator and you're trying to measure surface waves from much more local earthquakes, those signals would have a much higher amplitude, and a Trillium compact is perfectly acceptable for your needs. Another nice examples of system self-noise is looking at a composite PSD PDF of the entire EarthScope transportable array for its entire history. So again, we have power over here versus period or frequency. And if you look at the first percentile, so the very lowest noise recorded by the entire TA, you see it has this sort of interesting linear shape with frequency, with increasing frequency. And this is not produced by any physical ground motion process. This is actually shaped by the self-noise of the instrumentation that was used in the TA. So it had very consistent instrumentation. It's all Q330 digitizers and broadband sensors with very similar gains. And so you can see if you theoretically calculate that, sort of the self-noise of a Q330 plus other kinds of broadband instrumentation, that's the same, this gray dashed line here, as the first percentile of the TA. So this is not reflecting something physical about the Earth, saying, oh, this is the lowest noise that can possibly be recorded. It's saying, this is the lowest noise, this is a small signal that I can resolve based on the limitations of the equipment that I am using. So that's important. If you wanted to record smaller signals, you could install different instrumentation. So you can see that the Peterson noise model here, this black curve, is well below the TA self-noise floor, but that's because this was calculated using spectra from different instrumentation, and that had probably higher gains or higher bitrate digitizers, which are useful for global monitoring because they can pick up very, very small signals, but they will also clip on larger amplitude signals. They will clip sooner or exceed that system's dynamic range sooner than the instrumentation chosen in the TA. In the case of TA, they wanted to make sure that they could record local events as well. So they chose a different combination of instrumentation than you would use for, say, test band treaty monitoring, where you want to detect very small distance signals. Oh, I see a question about the smaller the mass, the higher the self-noise. Generally, yes, it depends a lot on other things in the instrument. But one way of decreasing, especially at long periods, the motion of your mass, sort of that wander with changes in pressure and temperature, is to just make it a larger mass.
Hey, Emily?
Yeah.
So is this trade-off you're discussing, is this something that's being improved over time with developments in instruments on the dynamic range versus self-noise issue?
Yeah, so it kind of depends. I mean, for most monitoring applications, a self-noise floor here is fine because you're trying to record signals that are, that are well above that self-noise floor. Let me get back over here. So this is looking at higher frequencies. This self-noise at long periods, this is something that people are working on. If you're making a sensor that is designed for the GSN, you want to have that self noise as low as possible if you want to observe very small signals like normal modes or earth tides. So yeah, instrumentation is constantly evolving. A lot of manufacturers are always trying to push it lower, but it depends on your needs. In some cases, you really don't need to have that low of a self noise floor if you're recording signals that are well above the self noise of your system. Yeah. Oh, here we go. Yeah, so old seismometers, right? They made huge masses, mostly in order to sort of pick up on different periods in their signals, right? So modern seismometers are complex electrical engineering masterpieces that use electronics to flatten their response and respond to a broader range of frequencies. This was not always the case. It used to be that if you wanted to record longer period signals, you just stuck more mass, you know, sometimes the size of a room in your seismometer. Okay, last thing I want to say about self-noise is if you are mostly used to working with data from permanent broadband sensors or say like the EarthScope transportable array or something like that, you may not think too much about self-noise. However, there's a lot of interest in the shorter period systems like Raspberry Shakes that have a geophone or nodes for very dense wave field imaging. Or if you are trying to use accelerometers, especially MEMS accelerometers, these kinds of instruments have self-noise that is much higher than you may be used to working with if you've sort of, if your instincts are developed for observatory grade broadband instrumentation. So you saw on that previous slide, most of your observatory grade broadbands have self-noise that is close to or very well below ambient earth noise at a wide range of periods. But if you're working with something like a geophone or a node, and you're interested in measuring ambient background noise, you may not be able to resolve it. If you're looking at background noise at a quiet site at periods of a few seconds, the self noise of that system may be similar to or even above the ambient noise at your site. And so you will only be recording basically the noise of your instrument system and not anything physically meaningful about the Earth. So if you are interested in using nodes, things like that, for different applications than the high frequency exploration that they were originally developed for, it's really important to know their limitations. If, for example, if you're trying to do moment tensor studies, which are usually at periods of a few tens of seconds, you're going to have a pretty big earthquake to show up on your node, and you don't know. I don't know if the frequency, the amplitude and phase response is very well characterized out at periods of tens of seconds, because that instrument is designed for higher frequency studies. So again, if it's important as you're moving into these sort of new and different kinds of instrumentation, know what amplitude you're trying to measure, know what frequencies you're interested in, and know what that instrument was originally designed for and how well it's calibrated, how well that response is known for the application that you're trying to apply it for. Okay, I did want to finish up the lecture part with a couple of follow-up questions from last week. Someone asked about channel naming conventions. So for example, for orientation, why do a lot of networks, all of the networks operated by ASL, for example, we name our components for a 3-component station. We use Z for the vertical and 1 and 2 for 2 horizontals, instead of Z, north, and east. And it may seem, I think for a lot of portable deployments, I know for Spree, for example, we named our horizontals north and east, and we made sure that they were always pointed north and east. However, there are a lot of cases where you can deploy a station without being able to orient it to true north. And so the reason that ASL uses 1 and 2 is we have a lot of borehole stations. And if you're down at the bottom of a 100-meter borehole, as you're lowering that sensor, it's suspended from a cable. It twists a little bit in space as it goes down, and we do not know the orientation of that sensor when it gets to its final depth and we lock it in place. The way that we measure the orientation of that is to set up a second sensor up top and measure the coherence. So we know the orientation of the sensor up top because we can very precisely measure that with a gyroscope. And then we basically do a similar process to how you would orient an ocean bottom seismometer. We look at the coherence between microseisms and we determine the orientation that way. So your one component might be pointed, 27 degrees off north, or it might be pointed south. Similar thing if you drop a station off of a boat and it sinks to the bottom of the ocean, you don't know its orientation, but you can measure it using the azimuth of surface waves from known earthquakes. So the best practice is to use the orientation that's specified in the metadata instead of assuming an orientation based on the channel name, because north is not always north. If you're in a region with a lot of iron-rich material, like northern Wisconsin, where we deployed spree stations, that will actually deflect the local magnetic field, and magnetic north is actually, several degrees off from true north. So if you can go back and measure it with a more accurate tool, you may want to change and update the metadata. In that case, it's better not to assume that north is pointed straight north. You always, the best practice is to obtain the orientation from the metadata and use that if you need to rotate your data.
Hey, Emily, I had a couple of questions about the horizontal
Yeah.
components. I recently experienced this when I wrote a rotation code and actually printed out the actual orientation information and realized that those stations that are named, N, or the components that are N and E are not always, azimuth 0, azimuth 90. And I was wondering, is there a sort of like threshold, like say you're at a 5-degree azimuth versus a 15-degree azimuth for your north component? Does IRIS go through and say, okay, like we're not going to call that north because it's this far off? Like, is there a certain kind of threshold, or could it be all over?
That's a good question. I don't think IRIS enforces anything. I don't think they inspect the metadata and say this is called north, but it's actually 17 degrees off of north. It's mostly up to the network operator to take care of that and determine what they want to call their station or call their channel. And it's about 5 degrees, I think, is the tolerance for, if it's within 5 degrees of north, you can call it a north channel. But that, I think, is a fairly loosely applied convention. I would be cautious about assuming that something called north is truly north.
Okay, and my second question that's related is, when it's Z1, 2, do those always follow like a right-handed coordinate system? Can we reliably say that they're always oriented like in the same way with respect to each other?
That is a good question. Again, I would always look at the metadata because you really don't know. I've seen some very funky things configured in metadata before. So I would say generally yes. I mean, if Z is up and you point the one component north, then 2 should be pointing east. But that's not always the case.
Thank you.
Yeah. Yes. Oh yeah, and as Suzanne just mentioned in chat, it can be very easy to make mistakes in the field. So STS2s, their orientation rod actually goes on the east side of the sensor. So you might have a sensor that is off by 90 degrees if someone tried to orient that to north. I know when I was deploying sensors as a graduate student, we got a sensor very nicely lined up with a north-south line, only to be analyzing data a few months later and find out that we had oriented the seismometer south. So in that case, we went back and renamed those channels so that they were Z1, 2, and then, I just described, okay, the one component is pointing at 180 degrees and 2 is pointing at 270. And if you find something like this and you are able to contact a network operator, I want to say we always appreciate that, because we do our own checks, but it's always, you know, independent quality control is always very much appreciated. Okay. Last thing I wanted to follow up on are channel naming conventions. So interpreting channel codes, there are some loosely followed conventions. Some people adhere to them more than others, but channel names are generally 3 letters. The first letter tells you the sample rate. So here are some examples. This link at the bottom will take you to a web page that opens up this some menus with a much more extensive list of channels for short period instruments and magnetometers and all kinds of things. But in general, the first letter is your sample rate. So you might see H, that's high sample rate. B is sort of an intermediate high sample rate. L is usually 1 sample per second. Or V, if you're looking at very long period data, that's 1 sample every 10 seconds, generally. The second letter tells you your instrument type. So I saw in the tutorial from last week, we were working with both velocity sensors, so broadband sensors, and some accelerometer data. So that middle channel code was an N instead of an H. And then of course the third letter tells you your orientation, north, east, vertical, or horizontals with some specified orientation. So if you see an LHZ code, you think, okay, this is a sensor, probably a broadband sensor, maybe a geophone, but proportional to velocity, right? It's not an accelerometer. It's the vertical component, and it's sampled at 1 sample per second. A different example, if you see an HN1 channel, that tells you it's sampled at a high sample rate. It's an accelerometer, and this is one of the horizontal components. So again, I encourage you to, if you see a mysterious channel code that you don't understand, a lot of the stations that I manage have barometer channels, and those have code LDO. You can go to this channel wizard and look and see what that might mean. But I do want to put the caveat on there that channel codes are more guidelines than actual rules. Again, this is not something that IRIS enforces religiously. So you might find, for example, a broadband sensor or a geophone sensor that is called BHZ, but more conventional naming might call it SHZ or something like that. So when in doubt, go get the response and look and see what's in there. Okay, so that is the end of my lecture. I guess we'll move on to the instrument response.
Emily, we have one final question before you wrap up.
Mm-hmm.
So the question is, a lot of stations downloaded from IRIS come with several, e.g. LHZ and BHZ channels for the same sensor. Is this just downsampled data?
Yes. Yeah, so if you have, you know, for the same location code, right? So if you have 00 data, that's the same sensor, and you might have a VH stream for people who are interested in high frequency data, and an LH stream for folks who are interested in lower frequencies. For accelerometers, a lot of the time, they will put out a constant 1 sample per second stream. So you'll see LN1, LN2, LNZ, and they will only record triggered data at high sample rates. And that's because accelerometers have really high self-noise floors. And so we don't want, you know, years and years of data that's essentially just self-noise. So we wait until we have a large signal, and then the sensor and the digitizer will take a few minute snippet of that sample at high sample rates and transmit it.
Okay, and we have one last question. So knowing the response corners for HH channels at high frequencies relative to BHZ, how low would you trust an HH seismometer in general?
Okay, so I guess if you could clarify, are you asking how high can you trust those frequencies, or
I'm for long period seismology.
Okay, yeah, so that has to do with the more the characteristics of the instrument that's used more than the sample rate itself, right? So you could have a really high quality or a sensor that's really, really good at long periods, like one of these Trillium 240s. Let me scroll back here a little bit. Okay, right, so you could take a sensor that's designed to record or that has a very long period corner, this Trillium 240, and the manufacturer also characterizes its high frequency response. And as a network operator, I run calibrations on these things every year to make sure that that high frequency response is really well characterized. So the sample rate doesn't have anything to do with the long period behavior of that sensor, right? So I could sample this Trillium 240 at 200 samples per second. That wouldn't be very useful if you're trying to look only at long period signals. If you're trying to find a signal that has a period of 200 seconds, you don't need 200 samples per second data. You only need 1 sample per second data. But there are folks who might be interested in using that station for higher frequency applications. And that's why we put out channels with different sample rates.
Sorry, I asked the question. It probably helps if I clarify this. So I was looking at the Canadian network, CN.
Mm-hmm.
They have, I'm looking at periods from 40 to almost 400 seconds.
Mm-hmm.
And the Canadian network has mostly HH channels, not a lot of BH channels. And I just want to expand my data.
Okay.
I was wondering how low can I go comfortably, even though I know that the curve is not really going to, it corners basically at like 100 seconds, right?
Right. Yeah, I think.
So I'm worried about the gain at the corner, basically.
Okay. Yeah. So pushing it to 400 seconds. I guess it depends. What type of signals are you looking at? Are these like teleseismic surface waves, or?
It's all actually body waves and surface waves.
Okay.
I'm doing full waveform CMT inversion at a global scale, and I use both body waves for mostly depth, and then surface waves to characterize the moment tensor itself. And I would like to go very low for higher earthquakes, for larger magnitude earthquakes. I would go to lower periods. So I basically have a filter that moves depending on the magnitude of the earthquake.
Awesome.
Yeah, so basically that's what I'm asking. Like, how low can I go? How low can I comfortably use an HH channel for high magnitude earthquakes?
Okay, well, yeah, so an HH channel, again, if that's the only sample rate that's available from your data center, if like you said, the shortest period you're working with is about 40 seconds.
Yeah.
I would decimate that to 1 sample per second, because you don't need that high frequency information.
Yeah, I'm doing that.
Okay, yeah, so you're doing that. And so then it depends on the type of seismometer that's used. You said you have something with 120 second period corner. So it'll depend on the amplitude of your signal, right?
Yeah.
I wouldn't try to get measurements on a magnitude 6 out to 400 seconds, but for an 8, sure.
Okay, all right. That's good to know, thank you.
Yeah, no problem. And so for this response exercise that we're doing, you could plot it up, and when you do your deconvolution, if it looks like you have a lot of long period noise in that 400 second region, even before the earthquake signal arrives, then you know that you're probably just blowing up ambient site noise when you do the deconvolution.
Yeah, okay, that sounds great. I'm just going to answer that question really quickly.
Yeah.
So basically what I'm doing is I'm looking at very long period waves because they constrain the moment tensor itself really well at long periods at global scale, because you basically sample the moment tensor with R1 and R3 with the surface waves that go once around the globe, and using very you can't use high frequencies for that because the surface waves just are completely dispersing all over the place. And so if you use higher frequencies than that, for these really far out arrivals, they just don't match with the numerical forward model data. They don't match with the observed data. That's why I'm doing that. I'm not usually, I mean, in general, I'm not going to 400 seconds. In general, like for, let's say, I usually do it for magnitude 6.5s, and then I go to a max of maybe 300 seconds. But that's like the absolute top cutoff, right? The flat response would be.
Yeah, I was just asking because you do run into issues with self-gravitation at these long periods. So I'm not sure if you're accounting for that, but we can have a chat about this later on.
Yeah, I'm actually aware. Good question.